All right, so as you work through the day 4 notes, I first want you guys to work on the warm-up. Spend a little bit of time working through this, and then I will explain my worked out solution. So pause the video, complete this warm-up, numbers 1, 2, and 3 on your own right now, and then watch the video to see the worked out solutions. All right, now that you've tried this on your own, I'm going to kind of take you through how I did this. To do that, first look at this. And so I'm looking at this and I'm thinking, circle Q is cut away. What is the remaining area of circle P? Well, circle Q has the center Q, so if I cut out circle Q, what is the remaining area? So we really don't even need to know anything about that sector yet. That's not a part of this. So I know that it's just the area of the big circle, circle P, minus the area of the small circle, circle Q. And this is my work for that. Area of circle P minus area of circle Q. The radius of circle P is 6. Which would make the radius of circle Q 3, actually vice versa. You know what the radius of circle Q is 3, and that would make the radius of circle P 6. And so my final answer, because it doesn't tell me what to round to, is 27 pi square units. The next one asked me for the area of the sector. Now I like to use proportions to find the area of the sector. Remember, to find the area of the sector, I need to know the measure of the central angle as well as the radius, so that I could figure out what the area of that big circle is. So here, it's the area of the sector divided by the area of the circle. Remember, the circle has a radius of 6, equals the ratio of the measures. So we have the central angle has a measure of 108 degrees, the whole circle has a measure of 360, and then when I solve that, I get approximately 33.9 square units, because we're talking about area. The next one says find the area between the 3 congruent tangent circles. So tangent, meaning they're just touching. And the radius of each circle is 6 centimeters. So I'm going to show you all of this work at once and kind of explain my rationale. So when I look at this, I know that segment AC, AB, and BC are all congruent, because if all the circles are congruent, the radii must be congruent. So each radius is 6, which makes the whole segment 12 centimeters long. And if each side is congruent, then it must be equilateral. And we know that if it's equilateral, it must be equiangular. So that's kind of my rationale here. So then each angle measure must be 60 degrees. The reason that helps is that in order to find the area of the shaded region, I'm going to take the area of this whole triangle and just subtract the 3 sectors. Now those 3 sectors are all congruent. So if I can find the area of the triangle and subtract the area of each one of those sectors, I'll be left with the area of the shaded region. In order to find the area of the triangle, I know it's 1/2 base times height. The base is just one side, which is 12 centimeters. The height, I use the 30, 60, 90 pattern here. Opposite 30 is my A. I know that's 6. Opposite 60 is A root 3. You could also use Pythagorean theorem, where you know that's 6 and that's 12. Pythagorean theorem gives us that 6 root 3. So area equals 1/2 the base times the height. And if I simplify this, I get 36 times the square root of 3. That would be the area of the triangle. I now need to find the area of a sector and subtract that from the area of the triangle 3 times. So the area of the sector divided by the area of the circle is equal to the central angle measure, which is 60, divided by the entire circle, which is 360. So the area of one sector is 6 pi. But I have 3 sectors, so I multiply that by 3, and I'm going to subtract 18 pi. Now I can't subtract these from one another, so I just leave it in parentheses, and my units are square centimeters. All right, now for number 3. Looking at number 3, we have a circle inside a pentagon inside of a circle. It says the radius of the larger circle is 9 inches. So a radius goes from the center to the edge, and I'm going to draw in a strategic radius. You could draw in whichever one you want, but I'm going to go to this vertex. And it wants to know the radius of a smaller circle. Now this would be the radius of a smaller circle, but I'm going to draw in a different radius. Because this right here is tangent, it can often be helpful to draw in a radius to that point of tangency, because we know that they form right angles. The reason that's helpful is now I know the radius of the larger circle is 9. I'm trying to find the radius of the smaller circle. I'll label that R. Now when I look at this, I know that this is a regular pentagon because all of the radii are congruent because you're in a circle, which means I could find this angle measure. So in my calculator, I'm going to do 360 divided by 5. That would give me the measure of one central angle. So if I did that, that's the measure of the central angle, but I want the measure of this angle, divide that by 2, and I get that that's 36 degrees. And if I use what I know from trigonometry, I know that if I have an angle measure and one side length, I can find another side length. So this is the adjacent side to 36. This is a hypotenuse. So adjacent and hypotenuse means I would use cosine. So I know that the cosine of 36 degrees is equal to r, the small radius, divided by 9, the large radius. Now I can use the exact answer or the approximate. This doesn't tell me what to round to, so I'm going to stick with exact. I multiply both sides by 9, and I get that the radius is equal to 9 times the cosine of 36 degrees. If you want an approximate answer, I can type in, make sure you are in degree mode, otherwise you're not going to get the same answer, 7.28, so it's about 7.28 inches, which makes sense because if this is 9, it's got to be shorter, but it doesn't look significantly shorter. So that makes sense. So I can throw in inches here or here. That's my answer. Now, let's say for some reason I decided to use this other angle measure, it's a little bit more work, but I can do it. I have 180 minus 90 for the right angle, minus that 36. This other angle measure is 54 degrees. And now r is opposite of 54. So opposite and hypotenuse would mean I would use sine. So I could say sine of 54 degrees is equal to the small radius over the large radius, which is 9. Still solve for r. A different exact answer would be 9 times the sine of 54 degrees. But if I put that in the calculator, 9 times the sine of 54, we get the exact same approximate answer. Those are equivalent. So about 7.28 inches. So either way, and don't forget the inches there. Those would be my two answers there. All right, so that was the warm-up, just kind of bringing in a lot of what we know about circles. I want to flip to the back, another extension of circles. A new vocab term for us today is segment, and I wanted to define what segment means. So a segment of a circle, the segment of a circle is the region bounded by a chord and the arc subtended by the chord. Let's talk about what that means. The segment of a circle is the region bounded by a chord. So I'm going to highlight first the chord. This is the chord right here that we're talking about. And the arc subtended by the chord. The arc that we're talking about is this arc right here. And so the region, the segment, is the region bounded by those. So the segment is this part right here. And it's kind of hard to see me highlighting in green, but it's the region in between there. I kind of think of it as the pizza crust. Like that looks like a piece of pizza to me, and so that would be the pizza crust. All right, so I want to have you guys take a little bit of time to work through example 1 on your own. I'll give you the blank is 8 centimeters. Try and work through it on your own, pause the video, and then I'll explain this one. All right, now that you've tried this on your own, let's take a look at it together. It says find the area of the segment of a circle with a central angle of 120 degrees and a radius of 8 centimeters, round to the nearest integer. All right, so if I'm drawing a circle, let's see how good of a circle I can draw. Okay, so we got our circle. And we have a central angle of 120, so I'll just draw that in. That looks like about 120 degrees. The radius is 8 centimeters, so I'll draw an 8 centimeters. That's 8 centimeters. But I want the segment. So remember the segment, you have the chord and the arc. So the area that I'm trying to find is this area right here. That's the segment, highlighting it in green. Okay? So as I'm thinking about this, well, in order to get that shape, what I'm going to have to do to find the area of the segment, I need to find the area of the sector and subtract from that the area of the triangle. So if I take the area of that whole sector and I subtract from it the area of that triangle, I'll be left with that green shaded region. So over here I'm going to show my work for the area of the sector. Remember the area of the sector, I'll just use a little pie piece there, is when I divide that by the area of the whole circle, I can set that equal to the ratio of the measurement, so that's 120 over 360. And when I solve this equation, I get that the area of the sector is equal to 64/3 pi. So that is the area of, I guess I should say square centimeters. That is the area of the sector. Now the area of the triangle would be 1/2 base times height. Now the issue is I don't know the base, nor do I know the height. But if I draw in that height right there, let's redraw this triangle. I now have a right triangle, and instead of 120, this is now 60. I know that because that is an isosceles triangle, and so that will be the perpendicular bisector. So that's a right angle, and that makes that 30 degrees. So that's 8 centimeters. So I need to find the height. Now, depending on what the problem gives us, we might find that height different ways. Maybe it's trig, maybe it's whatever, Pythagorean theorem, something else. But in this case, I could use trig. I could also just use my 30, 60, 90 pattern. So I remember opposite 30 is a, opposite 60 is a root 3, and opposite the right angle, or the hypotenuse, is 2 times a. Which means in this case that a, if 2a is 8, then a is 4. So the height of that isosceles triangle is 4. And the base, or half of the base, would be a root 3, so 4 root 3. So when I look at this entire isosceles triangle, if this is 4 root 3, and this is 4 root 3, then that entire base would be the sum of that, which would be 8 root 3. And the height is 4. So the area of the triangle would be 1/2. The base is 8 root 3 times the height of 4. And when I simplify that, I get that the area of that isosceles triangle is 16 root 3, and my units are square centimeters. So now the area of the segment will be equal to the area of the sector minus the area of the triangle. And if I put that in my calculator, I get that's approximately 39.3078. It asks to round to the nearest integer, so that's about 39 square centimeters. So for each problem moving forward, I'm going to need to find the area of the sector minus the area of the triangle if I'm trying to find the area of the segment. Each one is slightly different, and so how you find the area of that triangle or how you find the area of the sector might change. I'm going to give you the rest of the blanks right now, but you will, I'm not going to talk through all of the other answers. My worked out solutions are posted on the website, so you can look at my worked out solutions, but I would like you to work through these because every problem you see will be slightly different, and you got to be able to reason through how do I work through a new problem. All right, so for example 2, what's in the blank is area. Flipping to the back, example 3 is find the area of the shaded region. Number 4, what goes in the blank is area. Number 5, what goes in the blank is 80 pi. And number 6, what goes in the blank is 140 square feet. All right, good luck.